Okay, welcome everyone who's joining for this first talk of the third series of the One World ABC Approximate Bayesian Computation. Before introducing the speaker, for those of you that joined a little later, questions are very welcome. We're going to take them at the end of the talk. I'm going to you can write them in the chat and then I'll read them afterwards to the speaker. So today we have, as you see, Matthias Quiros is a lecturer at the Department of Statistics, sorry, at the School of Mathematics and Physical Sciences in Sydney, University of Technology, Sydney. And this work is co-authored with some colleagues, both in Sweden, Matthias Villani, and in Australia, right? Robert Cohn and Salomone. So, Matthias, I think that that you of course are very passionate about Bayesian computation, MCMC, and you've produced a string of work on subsampling, and this is I think a particularly exciting one because it targets non-IID observations. So thanks so much for being here and accepted to give this talk at this unusual time for your time zone.
Yeah, thank you so much, Umberto. So as Umberto said, this is joint work with Matthias Villani, Robert Cohn, and also Robert Salomone. So the title of the paper is Spectral Subsampling MCMC for Stationary Multivariate Time Series. So the challenge the challenges we face in these papers are two of them. So the first challenge is that when you have a time series model, you typically have a very expensive likelihood function that you need to evaluate. And the reason for this likelihood function being expensive is that you typically don't have any independence assumption that is appropriate. And you end up, like in the Gaussian case, you end up that you have to evaluate a big covariance matrix. You need to evaluate and invert a big covariance matrix. So one of the methods we use for this, the ideas to tackle this one, is that we work in the frequency domain instead. And as we will see in the frequency domain, you can formulate the likelihood that is much more computationally faster because you can rely on an independence assumption, at least asymptotically. I'll talk more about what I mean with this. And the second challenge that we get is that even in the frequency domain, if the time series is very large, it's still going to be a problem for us to do some Bayesian MCMC because MCMC, in particular with the focus of Metropolis Hastings, it needs to evaluate the likelihood in each iteration. And it's a sampling algorithm, so we typically require to obtain many samples, so we need to repeatedly evaluate this likelihood, which is a function of a lot of data points if we have very, very large data sets. And what we're going to use here is an idea called subsampling MCMC, specifically spectral subsampling MCMC, where we subsample observations in the frequency domain, and we estimate the likelihood within an MCMC using just this little subsample of the data. We have a paper, the Salomone et al. Paper here, which develops a spectral subsampling MCMC for stationary univariate time series. So what we're doing in the current paper here is that we make a multivariate extension of the method and the model that we have in this paper. So let's start with some basic stuff. So the spectral density of a univariate stationary process, the paper is multivariate, but I'm gonna present the things first univariately because it's always easy to do the univariate case, you understand that. And basically the multivariate case is just generalizations of these expressions to matrices. So the autocovariance function of a zero mean stationary process is defined as this. So it's a function here of the time lag of the time series, and it's the expected value of this product here. And the spectral density is just the Fourier transform of this covariance function here. So I have a simple example here when I have an AR process, and we can compute the covariance function. And if we take the Fourier transform of this one, this is what we end up with. And I'm just going to show very quickly here 3 different cases of this process. And the first case here, we see that we have an autocovariance function that decays, not too quickly, but not so slowly. So what we see here is that the signal in the time domain here, we see that it contains a lot of low frequency components. So the signal doesn't move too fast. So it contains some low frequency components, but it still has some high frequency components. So it's not moving too slowly. Whereas in the second row here, we see that this signal really consists of only low frequency components. So you get a really, really persistent signal. And this is also translated in terms of the autocovariance function, where you see that the autocovariance here decays really, really slowly as a function of the difference between the time points. And over here, you see a function that's a time series that's really oscillating. It's really, really erratic. And this contains of a lot of high frequency components. In the frequency plane, it's mostly represented by these high frequency components here. So the idea that we use to obtain this fast likelihood to evaluate is that we bring the data in the time domain. The likelihood is expensive. So what one does is that one brings the data from the time domain to the frequency domain and formulates a likelihood in the frequency domain. And the tool for doing this is the discrete Fourier transform. So the discrete Fourier transform is defined as this. So you see that this is your original time series, and then you have this exponential here. So I is a complex number here. So this is basically a weighted average here over the time domain data. And you do this, you compute these things for the so-called Fourier frequencies, and they are n of them, and they live between, if you plug in k equals n half here, you see that this one lives between minus pi and pi, because they are periodic functions, right? So they update, they are periodic with the periodicity 2 pi. So it's enough to look at the frequency in the span minus pi to pi. And you can compute this discrete Fourier transform using something called the fast Fourier transform, which computes this in this complexity. So it's pretty quick to do this. And the actual data observation in the frequency domain is going to be the so-called periodogram. So I'll talk a little bit more about the periodogram, but what the periodogram is that it's the modulus of the discrete Fourier transform. So this is a complex number. We take the modulus of it and we divide here by the number of frequency points that we have. And this is going to be the observation, the kth observation in the frequency domain. So our data went from the frequency, from the time domain to the frequency domain. So in the time domain, we have time series data. In the frequency domain, we have this periodogram data here. So what's really nice about this periodogram data is that you can show that as you get n goes to infinity here. These guys here are going to be asymptotically independent of each other, and they're going to be random variables which have a distribution that's an exponential distribution, where the expected value of that exponential distribution is equal to the spectral density of the model. So this is the spectral density of the model that we have here. And obviously, this is just like, you know, heuristically, the steps that you use is obviously there's quite a lot of things involved in showing this, but just to give you an idea where the exponential form comes from, is that the DFT itself is asymptotically complex Gaussian because it's a central limit theorem. You can apply a central limit theorem to derive this. And the modulus here is going to be a sum of two squared independent Gaussians. And we know that when we square independent Gaussians, we get chi-squared variables. And if we add two of these, we get a chi-square random variable with 2 degrees of freedom, and we know that that one is related to the exponential distribution this way. So once we now know that we have independence, and we have the actual distribution of these periodograms, we can formulate a weighted log likelihood really easily, because we know the density for this one, and in the log scale, this just becomes a sum over all frequencies. And what you guys should note here is that this is the periodogram data, and here is the spectral density. And this approximation here is called the Whittle's asymptotic approximation of the log likelihood. It can be biased for small n, but we only consider large n, because it's only when we have large n that it's actually relevant to do subsampling. So unlike the time domain, the Whittle log likelihood is a sum. So that's why it's fast. It's a sum. And what you can do when it's a sum is that you can apply this so-called subsampling MCMC scheme, which basically just subsamples the frequencies. So it subsamples a subset of the frequencies in each MCMC iteration. And then based on those frequencies, it estimates this sum for the whole population of frequencies. And what's really nice here with the periodogram is that you only compute it once before the MCMC, because this little thing here doesn't depend on the model parameters. You can compute it once for the MCMC. And then we use the framework in this paper here to do the Metropolis hasting. That's what we do in the Salamoni et al. Paper. And in the Salamoni et al. Paper, we consider something called an autoregressive tempered fractional integrated moving average process. So I'm not a big fan of acronyms, but of course, you know, if I'm gonna say autoregressive tempered fractional integrated moving average every time I say this model, I'm gonna run out of time pretty soon, and my slides are just gonna be cluttered everywhere. So I will use the term ART-FEMA for this, okay? So T for tempered, F for fractional, and I for integrated. This from this paper here. And what we do in the current paper that I'm presenting now is that we propose a vector extension of the ART-FEMA model. So we call it vector ART-FEMA, and instead of saying the whole expression here, I'm going to say VART-FEMA. Okay, and it's basically just a multivariate extension. And why would you do this thing? It turns out that you can model semi-long memory properties. I'll talk a little bit about what I mean with this thing here. So this model that we propose, you can use it for modeling multivariate time series that have this semi-long memory. The ART-FEMA model itself, it nests the ARIMA model. So the ARIMA model is basically that you take the integer differences here. So for example, if d is equal to 1, what you do is that you take the first difference and you fit a standard ARMA, autoregressive moving average model, to the first difference of the series. And what the ART-FEMA model does is that it generalizes this to fractional differences. So if you see what we're doing here, we're introducing this so-called tempering parameter, and we are now allowing for d to be fractional. So it's not integers anymore here. It's actually fractional. So by using I think it's called the fractional binomial theorem or something like that, this operator here is defined to be this thing here. And what you see here is that this is sort of going like it brings the history of the process with it. So we can understand why we would use this to model series that have a longer memory. So this nests really famous models. It nests the ARIMA model. So if we say that lambda is equal to 0 and d is an integer, and it also nests the so-called ART-FEMA model. So the ART-FEMA model is the fractional differencing, but without tempering. And it can be shown that that model is stationary if this fractional differencing is to its absolute value smaller than a half. And this has so-called long memory. This is a long memory time series model. And in a long memory time series model, what you get is that you get a covariance function that dies off so slowly with the time lags that it's not, when you sum it from minus infinity to plus infinity, you get a divergent sum. Okay, it decays really, really, really slowly. So let's look here a little bit at the role of this tempering parameter that it's introduced in this model here. So it's a parameter that's positive. And And what it basically does is that it allows you to have long-range dependencies for a number of time difference here. And then it makes the beyond that time step, it gets an exponential decay of the covariance function. So you actually get that the process becomes absolutely summable in its covariance function here. And if you have the usual conditions on AR and MA parts for stationarity, you can show that for all these that are not integers, and if the tempering parameter is greater than 0, the process is actually stationary. Of course, again, I stress that these two parts need to be stationary as well. And this is the spectral density of this process here. So if you've done some time series, what you'll know that if you have the standard ARMA model, this is the spectral density that you get. So when you're sort of modeling this tempered fractional differencing part, what gets added to the spectral density is this part over here. Okay. So if you understood what I've presented so far, you basically have understood what you need to understand, because what I'm going to show you now is just a multivariate extension of these ideas. So the expressions are going to become a little bit different obviously compared to what I showed you, but you can just see it like basically as matrix generalizations of what we had before. So we're going to talk about an autocovariance matrix function. So now xt is a vector of dimension r, and it's going to have an autocovariance matrix function. The spectral density is now going to be a matrix itself. It's still going to be a Fourier transform, but this one is going to be a matrix now. And the off-diagonal elements of this matrix is what we call the cross-spectral densities. And instead of going with the usual discrete Fourier transform, we're going to make the multivariate. We're going to compute a multivariate Fourier transform here. But notice that it's really, really similar to what we had before, but now this guy is a vector. The DFT, the multivariate DFT, is asymptotically independent complex normal. So now this complex normal here is a multivariate one, because notice that this is the covariance function here now. The covariance is the spectral density matrix here. If we compute the multivariate periodogram, it's going to be a complex Wishart guy. So this is the conjugate transpose. And we can now formulate, so we're not too surprised that we see a Wishart coming here, because remember that in the univariate case, we have a chi-squared, and basically the Wishart is a multivariate generalization of the chi-squared. And the multivariate with the likelihood we form now has this form here. So this comes from these guys being the Wishart distribution here. And as you see, it is still a sum. So we can still apply subsampling MCMC. So we're now going to propose the multivariate extension of this univariate process, the Artfima process. And if you have a look at this expression here, and if you forget about what's here, you would recognize this as a vector autoregressive moving average model. So the one that it's very famous in econometrics, I think. A lot of people use this. So what's happening here is that we're introducing this operator here. And this is a tempered fractional differencing matrix. So you see here that this is a diagonal matrix where each of elements in this diagonal here resemble a lot the univariate case, right? So now we are allowing the model to have, for each time series, one tempering parameter and one fractional parameter for each of the time series. So I think I've already said that. We know that Artfima nests ARMA, so obviously Artfima nests the vector autoregressive moving average one. And we can derive the spectral density matrix That's theorem 1 in the paper. The spectral density matrix looks like this. Okay. So I think that if you worked with multivariate time series, you might recognize a few of these expressions coming up here when you work with vector autoregression, so vector moving averages or vector autoregression moving averages. Okay. I'm going to ask a few questions that are of interest here, and then I'm going to show you the results. So the first question is that, is this proposed vector ART-FEMA model better than just the vector ARMA model? That's my first question. My second question is subsampling MCMC for the multivariate with a likelihood accurate? What I mean with that is it accurate compared to if I would use the multivariate with a likelihood using all data? So if I subsample the multivariate with a log likelihood, do I get accuracy in terms of that I can estimate the multivariate with a likelihood for all data? That's the second question. But there's a third question here that's really interesting, because remember that I said that I called it Whittle's approximation, and well, it's obviously an approximation. So one question is also, how accurate is the multivariate Whittle approximation to the true posterior? And what I mean with that, I just mean a posterior that is based on a likelihood that is computed in the time domain. So one little problem with question 3 here is that the time domain likelihood for the ART-FEMA model with a large data set is intractable. We cannot compute it. So what I will have to show you the empirical results of, it's that I can only test this question or answer question Q3 using a vector autoregression moving average model. So instead, I'm going to show you the results here for question 3 using Varma. And finally, question 4 is, how much faster is subsampling compared to using the multivariate with a likelihood on the full data set? Okay, so how much do we actually gain by doing this subsampling stuff? I'm going to have 3 applications that I'll show you. So the first application is a water velocity. So it's from hydrology. So there are 2 locations in a river in Michigan, Sunnygow, I don't know how you pronounce that. And these rivers are 20 kilometers apart. And the sampling frequencies of this series is that we record data every 12 minutes. And we have 2 time series, and each of the time series have 24,000 observations. So this is the smallest data set that I'm going to be presenting. So remember here that this one is the smallest one, because I'm going to show you something later that I think might be related to that we have a small-ish time series. And these are how they look like. This is the first location, and this is the second location. You have time here and the velocity on this axis here. The second application is Swedish Temperatures in 3 different airport locations. Arlanda, which is in Stockholm, and as well Bromma, which is in Stockholm, where I used to live when I was in Sweden, and Landvetter, that is pretty close, I guess, to where Umberto is living in Gothenburg. We remove trend and seasonal components, and after doing so, these are the 3 series that we have, and we have 32,000 observations on each of these series here. Okay, so this is how the temperatures look like. And the final application that I'm going to show you is some air pollution data from Stockholm. So we measure 2 pollution types, so nitrogen dioxide and particulate matter, and we measure these also in 2 different streets in central Stockholm. So this is a 4-dimensional time series. And we analyze the time series using these transformations here, and we filter to remove some trends. And the sampling frequency for this one is every hour, and here we have 50,000 observations for each of the time series. And it looks something like this. Umberto, I'm doing quite well on time. How much?
Well, you asked me to alert you 10 minutes before. I mean, you have 18 minutes or so, I would say.
18 minutes. Okay, that's great. Thank you. Okay. So I've shown you the 3 applications, and I'm going to estimate to answer the first question here. Remember that the first question is the Vartfima model providing anything on top of what the Varma model is doing for us? So I'm going to estimate both these models. And in order to do model selection here, what we're going to do is that we're going to compute the BIC approximation of the log marginal likelihood to evaluate these models. And we're going to use what's quite standard prior when you do Bayesian analysis on these kind of vector autoregression moving average models, which is called the Minnesota style prior. So it's a prior on the AR and MA coefficients, and it has a diagonal covariance matrix where you put these kind of variances on the diagonal. And the idea is basically that you want to shrink parameters that correspond to longer lags more. And you also want to count for the fact that you have more within each series. You want to shrink the parameters less compared to what the influence from the other series. You want to shrink the other ones more. And to facilitate MCMC sampling, there's a quite hard condition on the AR and moving average models to obtain stationarity. So we don't want to propose something and then move to a place in the parameter space where the process is non-stationary, because we will be rejecting a lot in our MCMC. So we use a parameterization that ensures that we can move on an unconstrained space. And then the inverse transformation of that ensures stationarity. Okay, so you will only propose parameters that obey the stationarity condition. So this is a table of a lot of marginal likelihoods here. So the higher the value here, the better. So let me explain this, what I have here. So first of all, I have 3 data sets. And what I have on the left part here is how many lags do I include in the autoregressive part and how many lags do I include in the moving average part. So 1 and 0 means that I have 1 lag on the AR, 0 on the moving average. If I look, say, at 1, 1, it means I have 1 lag on each of these. And the TFI is that we do the tempered fractional differencing, and the no TFI is that we don't do it. So this is the ARMA, the vector ARMA model, and this corresponds to our model. So the first thing I want you to notice here is that you will always gain something by doing this tempered fractional differencing. So for every value that you find here, you find a value on the right-hand side that's better. And sometimes you can have, if you look, for example, at the moving average, so there's no autoregressive component for the temperature, you only have a moving average. And if you only fit a vector moving average, you get quite a bad result. But if you include the tempered fractional differencing, it improves significantly. So the answer to question 1 is yes. Tempered fractional differencing is better than no tempered fractional differencing, according to these measures here. The second question was, is subsampling the Whittle likelihood as good as computing the Whittle likelihood for the whole data? And what we see here, this is for the water velocity example, we see that this is quite okay. So the dashed line here is the subsampling, and the solid line is the corresponding full data version. So you see here that for all the parameters we're plotting here, it doesn't look too bad. So this is for the first data set, the water velocity one. I have something for the second data set here, which are the temperatures. And then I have something on the final one for the pollution data here. So what I have within parentheses here is how many parameters are there in total in the model. So in this one, we're fitting a quite complex model here with 47 parameters, and we can still run the subsampling MCMC and get quite okay results. The next question was, how good is the Whittle likelihood approximation to the true posterior, where the true posterior was based on the time domain likelihood? So remember that I said that I had one data set that was smaller than the other ones, and that's what I'm showing you here. So this discrepancy here is very likely because there is not enough data in this model here, because the Wheeler approximation is an asymptotic approximation. But if you look at the scales here, it's not too bad. It looks horrible when I plot it like this, but if you start looking at the numbers, it's not too bad. Like, you know, this is differing on the third decimal. So it's not too bad if you really pin down these numbers here, it's not too bad. But for the other examples, it looks significantly better. So when we have a little bit more data, you see here that the orange one, which is the time domain likelihood, is on top of, the Whittle approximations are almost on top of that. Okay, so it's really accurate here for this application. And over here, it's also accurate for the pollution data with 42 parameters. So one thing that you might be able to spot over here is that this one looks like a little bit weird here, but I think that this is mostly due to mixing problems in the MCMC, if I would take a guess. Because the thing here is that we're sampling in a really, really complex posterior in a quite high dimensional space, and we're just using a random walk proposal. Okay, so we're using a random walk proposal that we adapt to the standard optimality conditions that are 0.234 thing. And the final question that I want to answer was that one of the speed up of the subsampling MCMC. So I'm going to define the relative computational time here, which is the computational time of the MCMC using the full sample relative to the computational time of the spectral subsampling MCMC. So using the subsample of the data. So if this one is equal to 1, that means that the all algorithms are equally fast. They're performing equally fast. And if this number is, say, 10, it means that our algorithm is 10 times faster. And these computational time measures, they are accounting for two things, basically. So they are accounting for how well the chain is mixing, and they are also accounting for how expensive is it to compute the likelihood. And how expensive it is to compute the likelihood, we measure that thing using the number of density evaluations. And the reason we use this measure is because it's usually the standard measure people use in this literature. And it also makes everything dependent on the implementation, independent of the implementation. Okay, because you can always look up a C guru or something that will implement a subsampling algorithm really fast for you. So these are the three data sets. These are the three top models that I had. And what I see here, for example, for water velocity, I see that the mean, the minimum, the mean, and the max, they're over the parameters. So we have about 11 parameters or something like that. So the minimum improvement here for each parameter, for the minimum improvement was that we were 97%, 97 times faster. So 970%, so 97 times faster. And the maximum was 133 times faster. So for the Swedish temperature, there was a bigger model. And we were between 82 and 110 times faster. And for the Stockholm pollution data, we were between 81 and 114 times faster, depending on which parameters you're looking at. And like I would say, on average, the method provides 100 times speed up for the examples that we have considered. Okay, so let me sum up what I've been talking about. So the width log likelihood is fast to compute compared to the time domain log likelihood. And this is regardless if you do subsampling or not. I mean, you can use the model that we're proposing in this paper here. You don't need to do subsampling. Subsampling is just speeding up on it further. Okay, but one of the real keys here is like, even if you don't do any subsampling, the thing is that you want to bring your computations to the frequency domain, because they're much faster there. Another good nice feature with the width log likelihood is that it's a sum, which makes it really easy to subsample. And the way the algorithm works is that we subsample periodogram observations, so really periodogram matrices in the multivariate case. And we extended the subsampling MCMC approach to this multivariate time series now. We've shown very large speedups compared to regular MCMC. So with regular MCMC, I just mean an MCMC that uses the whole data set in its computations. We propose this vector autoregressive model, the vector arch-FEMA model. It's a multivariate model, and as I said, it's good for modeling time series that have semi-long memory properties. And we've shown that it's provided significantly better fit than the versions without the TFI part, for 3 real-world examples in hydrology, meteorology, and also environmental sciences. So one thing that's in future work, so what I was really like just saying that it's a sum, we can subsample it, it's easy. But really the reason why we can subsample it is because we're using efficient control variates in our subsampling MCMC algorithm. In this example, we were actually able to fit the model even in a 47-dimensional space. So it was quite amazing that we could construct a control variate for such a high-dimensional model. But if it's there's also a reason why I only showed you examples that had up to 4 time series. Because say if I would take, say, 10 time series or something, I end up with so many parameters that there is no way that I can, using the techniques that we have currently, there's no way that we can have good control variates for that many time series. And what we're also working on is that we want to make a sort of a space, we want to use these methods to do subsampling on spatially dependent data sets. And that's it for me, so I can show you the paper. So I've put the slides on my webpage if you want them, and I also have a Twitter handle, so I put them on Twitter. Here's my Twitter handle. I guess that Umberto is going to upload the slides in the page as well for the seminar series. I'm happy to take questions, but first of all, let me just show you the paper that I was talking about. So this is the paper. And you can find it on arXiv.
Thanks.
Yeah, thank you.
Thanks, Matthias. Thank you very much, very much. That was a perfectly timed talk and very, very, very pleasant to look at. So I'm going to stop the recording, so hopefully everyone will feel free to to open up the discussion without any worry.